Good afternoon, everyone. I'd like to thank you all for joining us today in our continuing education series. Today our featured topic is on connectors, the types and polishes. My name is Jessica Petrohoy, and I'm the marketing coordinator at fiberoptic.com. Fiberoptic.com is the leading provider of fiber optic products, training, and rental equipment. When choosing a connector, there are some things that you need to consider. For example, loss, reflections, repeatability, ease of installation, and cost. In this webinar, Terry Power will discuss these connector issues, the types of connectors, and the polishes used to reduce back reflection. So at this time, I would like to introduce Terry Power. Terry is one of our senior instructors and an outside plant technician with over 25 years in managing networks. When Terry is finished, we will be taking questions from the GoToWebinar chat box. Thank you again for joining us today, and at this time I will turn the presentation over to Terry.
And good afternoon, everyone. Again, this is Terry Power. I'm senior instructor and one of the primary traveling instructors here at the Fiber School at fiberoptic.com. And as for 25 years in the field, I started doing cable television in 1987. Over the years, made the transition completely from coax into fiber. And by 2007, I was outside plant coordinator for Tele Barbados. And then in 2009, came to work here at fiberoptic.com, running crews in the field, and then ultimately moving over to the training division full-time and becoming senior instructor and international training coordinator. So, with all of that said, connectors, types, and polishes. Alright, so today we're going to talk about an overview of connectors. Then we're going to get into talking about the types of connectors from the standard through to the small form factor. And then we're going to talk about polishes with the PC and APC connectors and all the polishes in between. So the overview. Now all connectors have essentially the same components. We're going to start at the bottom actually, and we're going to go look at the ferrule. And the ferrule in my mind is where the magic really happens. This is the precision component that allows for the precise alignment of the two fiber core axes. On both sides you've got a ferrule. In the center of it is 125 micron cladding, and within that in single mode is an 8 micron core. And the precision of these ferrules allows for those two 8 micron cores to line up perfectly and allow for the transmission of light with very low loss and very low reflection. Now, that's bordering on magic in my world. So then you have within the connector mated pair, you're going to have the coupling device, whether you call it a bulkhead, barrel, or just simply mating sleeve or coupler. You're going to have this device here, the alignment sleeve inside aligns the two ferrules so that that precise alignment takes place. Now moving back into the connector itself, you're going to have the connector body. In this cutaway view, we're looking at an ST connector. And that's going to be the bayonet style, but the connector type, each one is going to have its own connector body where the connection takes place into the coupler. Now behind that is going to be whatever retaining ring holds it all together. And then behind that you will see in this cutaway that there is a place where the bare fiber all the way down to the 125 micron cladding is stripped bare and inserted into the back side of the ferrule, creating a very weak spot here. And that's why we have the strain relief boot or bend relief boot, depending on what you want to call it, But the idea is that this boot will keep that from bending over and shattering at that very weak spot. Now, the ferrule, we're going to return to talking about the ferrule before we move on. The ferrule is most commonly made out of a polycarbonate plastic. Those are the less expensive connectors, and they've got performance parameters that are meeting all of the standards. They may not be the best, but they're certainly going to meet the standards, and unless you've got very, very tight tolerances, most of the time the plastic ferrules will be okay. Now the steel ferrules or other metallic ferrules are something that you typically only see now in military applications. And then lastly, the ceramic. Now by all accounts, the ceramic material for ferrules is the material for ferrules. They can get quite costly, but if you've got very tight tolerances and not a lot of room in your loss budget, the ceramic ferrules are definitely the way to go. Now they're going to have the lowest loss and the highest performance standards of any of the ferrule materials. Now, with all of that said, you're going to select the connector that's best for you. There's a lot of considerations, and we're going to go through about 6 of them and how these would apply, and they maybe help you to make that selection. Cost. The cost of the connector itself. Again, the plastic polycarbonate ferrules are going to be much less expensive than the ceramic. Installation cost. That goes to materials. If you're using hot melt, you have to have the oven. If you're using 2-part epoxy, you have to purchase the epoxy materials. So all of that needs to be taken into consideration. You also need to think about how long it's going to take. And kind of jumping around on this page, time also goes to installation cost. How long are you going to spend building the connector onto the bare glass? And that's part of your installation cost. Ease of installation goes to the type that you're using and how easy it is to install, as well as the connector density within the patch panel. How many fibers do you have coming into the comms room? How tight do you need to get them? And we're going to look at density issues in later slides. Loss budget. Loss budget is going to have a certain effect on the connector style. Some, while all are going to meet the standards, some do a better job. That's going to go back to the ceramic ferrule versus plastic. Most people think that the SC has a very low loss compared to other types, so you might be looking at that, at the type of connector as well as the material for the ferrule. Now, size. The standard 2.5 millimeter ferrule and the small form factor, whether they're the 1.25 or they're kind of duplex styles. We're going to talk about each of those, but that's going to come down to density issues as well as did the ease of installation. Now, repeatability is the ability to disconnect and reconnect and get essentially the same loss. And that standard and specification is pretty small for the amount of difference that's allowed, and most connectors will have a pretty good repeatability. I think that LCs in the small form factor world probably have the best repeatability standards, than SC after that. And again, we get back to time. Anaerobic style is your 2-part epoxy. Or you've got the hot melt style. Now, a lot of people have preferences one way or the other. I personally have found that the hot melt works pretty well for me, but other people are just as quick to tell me that those are worthless and that they prefer the 2-part epoxy. I've used both in classrooms and in certain applications, and I really don't see a difference. I just find the hot melt personally easier to use. And then when we're talking about time, I would be remiss if I didn't talk about the quick termination style of connectors. And these are going to be the factory polished connectors with a mechanical splice essentially in the back side of the connector. And then you just strip, cleave, or clean and then cleave the connector, or the fiber rather, and insert it into the back of the connector, and there's a mechanical connection that holds the fiber in place. And we'll talk in a little more detail about quick turns in a later slide as well. All right, connector types. We're going to talk about the standard connectors, the ST or Sam Tom, FC or Frank Charlie, SC, Sam Charlie or subscriber connectors. We're also going to talk about the small form factor connectors, several of them, MU, MTRJ, LC, MPO. All of those are smaller, more compact connector styles or connector types, and we're going to talk about those as we go along. Now, the ST or Sam Tom, now I never did remember these. I always struggled with this. You know, ST and FC and SC and Sam Tom and Frank Charlie, and oh my God, the alphabet was just making me nuts. And then someone helped me to come up with a little way to remember them, and we use these in our classrooms here. ST is that style that has the little bayonet stobs on it, and all you do is stab it in and twist. Hey, that's pretty good. Stab, twist. ST. That I can remember. Let's see, the FC, that's the one with the threaded post. So I'm going to turn that in full circles. FC, full circles. I can remember that one. SC, I just stab that one in and it clicks. And that's the easiest way for me to remember them. And I hope that helps you guys out a little bit. Let's see. Let's return to the top, though. I digress. Sam Tom or ST connectors, stab and twist. They're used in multi-mode and single-mode applications. Typically, you'll see them in the local area networks, and they're relatively common. And they have a spring load on the back and the bayonet plug that we talked about. FC is typically in a single-mode application. It's comes over from the telecom world, and it screws down with that post, multiple threads, and it screws down pretty tight for a real good tight connection. And then the SC or subscriber connector, it's used in both multi-mode and single-mode applications. You'll see it in telecoms, local area networks. In fact, you're starting to see it turn up in just about any application for fiber optics. Now, you will notice on this slide that there's a mention of a non-optical disconnect on both of these. Now, the non-optical disconnect is when the two ferrules are allowed to back away from each other, causing an air glass boundary. It's going to cause loss and reflection. Now, while FCs and SCs do snap in or screw in pretty tight, in certain high vibration environments, they can be backed out slightly. The two ferrules can separate, giving you that non-optical disconnect situation. Because of the spring-loaded ferrules on the STs, they don't suffer as much from that in high vibration environments. So they're going to provide you, like on highway projects, we were doing some work for NJDOT, working on their ITS or intelligent sign systems. And all of their boxes along the interstate were using ST connectors because the vibrations wouldn't shake them loose. So you're going to see those kind of stick around a little bit. That is an advantage. On the other hand, if you're pulling on the back of the patch cord itself, you can pull that ferrule back and induce a non-optical disconnect if you're not doing good slack management. You can induce that with the ST connector because it is spring-loaded. You can pull it back. But in most cases, that positive pressure is going to be maintained and not vibrate loose. So I've already talked a little bit about this aspect of it at the bottom of the screen. It's declining in popularity. The ST connector is going to ultimately, I think, be phased out, except in those high vibration environments where that spring load positive pressure is an absolute necessity. Most commonly used in multi-mode applications is the IEEE 802.3 standard connector, and that was one of the first adopted standards. It is round with the locking tabs, 2.5 millimeter ferrule, and was first developed by AT&T. Now, the FC connector has historically been used in single-mode applications. I believe it's because it looks like an F connector. That's probably where FC comes from, and it's probably why it was so popular in the single-mode outside plant world, because, you know, all us coax guys are used to screw-on F connectors. So they made connectors that looked like what we're used to. Those screw on for a very firm fit. It is being replaced by SC and LC connectors. And I think one of the reasons for that is that you simply can't get your fingers in there too tight. You start moving these connectors closer and closer together to get the density we need in this day and age. We're finding that, you know, my hand particularly, you know, my big old sausage fingers, I can only get so tight, or so, you know, get around that connector with the connectors so tight. So I really like SC and LC connectors for that reason. So telco market, 2.5 millimeter ferrule, and it does have the best pull-out strength for the connector itself because of that threaded, screwed down tight connection. Now, the most common that's in the world today is the SC. Subscriber connector, stab and click, whatever helps you remember it. It snaps in and out. It is the EIA-TIA 568 C.3 standard connector. We start getting into some color codes because, as we said in previous slides, this is used a lot in both single and multi-mode applications, whereas the other two tended to be one or the other. In this case, we need a color code to help us keep up with what we're doing. And the blue connector is going to be single mode. The beige connector is going to be multi-mode. Now, you also see in this graphic that red connector, they also have some orange connectors, and typically what we see is those are for critical circuits. It might be fire alarm circuits or something like that that they don't want you to disconnect without thinking about it. In military or civilian contracting, military contracting rather, applications, I have seen the red connectors used for top secret, orange used for secret, yellow used for classified, and then just the standard connector color used for unclass. And in all cases, those non-standard colors are to make you walk up there and you see the color and go, wait a minute, I don't think I'm unplugging this until I'm positive. And that's all it's really there for. It's just a flag to make you stop and think. Now, these do have the standard 2.5 millimeter ferrule, probably the lowest loss characteristics of any of the standard size connectors, and pretty good pull-out strength. Because it snaps in so tight, it's not going to pull out before you break the connector apart. So, anyway, that is the standard connectors. Now, the small form factor. As I mentioned in that very first slide, we're worried a lot about density. More and more and more fibers going into communication spaces that aren't getting any bigger. Data centers, premise cabling, telecoms rooms, FTTX infrastructure. You know, all of these, we're putting more and more fiber into the same space. How are we going to do this? We can only get so tight on the standard size connectors. So, The small form factor connectors provide that answer. Most of them are approximately half the size, and we can get twice as many of them into the same space as we had for one standard size connector. We can double our capacity in one changeout. Double our capacity in the same amount of rack space. Now there are a number of styles of the small form factor. Let's see, again, there more and more fiber going to telecoms rooms. We need to get the compact connectors in there so as to provide the extra density. These being about half the size, we can get twice as many in. Typically they have a 1.25 millimeter ferrule. Some of them are duplexed, and we'll talk about some styles on the next slide. Now the V45 Volition was designed by 3M, and it uses a two-part plug-in socket configuration. It does have one cool feature in that it's got the 8-degree angle, like one of the polishes we'll talk about in the next section. It's unfortunately one of those proprietary things that you don't see as much in the field very much anymore. MTRJ, I'm going to skip one and come back to it at the end. The MTRJ was designed by AMP. It is the smallest of the small form factor. It uses two fibers that are spaced 0.75 millimeters apart, and it's usually intended to be a duplex connector. Now the MU, designed by Tyco, it is almost exactly an SC connector shrunk. And it fits into the same space. Two of these will fit into the same space as one SC. Again, the problem here, and the problem with all of these really, was the size of our fingers. And we're trying to make these smaller connectors that we can pack in there tighter and tighter, and we still got to get our fingers on both sides of the connector. We're still not winning. Now, let's go back to the LC. The LC, because of the way this is designed right here, I can get my fingernail, push it in right there, and unplug the connector. Now, of course, it's going to snap back in very easily as well, and I can push back here and snap it back in. So we can get these a lot tighter. Now, typically what you'll see, it is a lucent connector. It's very simple style, has the 1.2 millimeter ceramic ferrule, and they can be spaced out as close as 6.25 millimeters. It has the lowest loss of any of the small form factor connectors. And that's why, you know, that and the density capabilities is, I think, why it's taken the small form factor world. It's become almost the standard in the small form factor. It's easy to work with, and the mating sleeves are bulkheads. Actually, there's the bulkhead for two SCs, or LCs rather, two LCs. It goes exactly into the same spot on a front panel that one SC did. Exactly the same size, so you can pop out the SC bulkhead, put in an LC bulkhead, and double your capacity in an afternoon. A little bit of splicing involved with the pigtails, getting all the pigtails in the back switched over, but the rack space itself can be converted in an afternoon. And that is huge when we're looking at that previous slide and all of the density issues that we're finding in more and more places. Let's go through these one at a time with a little bit more detail. The MU, it's half the size. It's got a push-pull design and a free-floating ferrule, much like the SC, and it does have that 1.25 millimeter ferrule. MTRJ is the one we were talking about. It's automatically duplexed, and you can see the end of the connector here. You can see the duplexing and the two ferrules that are 0.75 millimeters apart. Now LC, I think we covered pretty much everything on this slide already. I do tend to get ahead of myself sometimes when I'm looking at a slide, and I'll say everything about the LC, and then I get to a slide where I've got the information written down. The ferrule is 1.25. It can be either UPC or APC end face, and we'll talk about those polishes here in just a minute. It is the lowest loss. It's a great little connector. It's going to have the lowest insertion loss and the lowest reflections of any of the small form factor connectors. In fact, it's comparable to an SC connector for loss characteristics. And lastly, I'm going to talk about an MPO. And, you know, the size of this, I'm not quite sure it qualifies in my mind as a small form factor. But what it does is that multi-fiber push-on allows us to do something. The most common way you'll see it is pre-connectorized drops in the FTTX world. And if I can send someone out with a pre-connectorized drop that they can just pull the drop through conduit, plug it in at a distribution hub on one end and plug the other end into ONT at the house, then I've saved a ton of money and time. No splicing in the field is necessary. Now, the multi-fiber push-on is covered by a couple of standards. The IEC 61754-7 is the international standard, and the EIA-TIA 604-5 or Focus 5 is the U.S. standard. Now, as promised, I'm going to talk about the no polish or quick termination connectors. They are mechanical splices built into the back of a connector. There's a stub of fiber that is already inserted into the ferrule, scribed, cleaved, and factory polished. So it's going to have, you know, the best end face you can get, and the stub's going to be in the back of the connector with a pocket of index matching gel. And all you're going to do is strip your fiber, clean it, cleave it. The order in the slide's wrong. You always clean before you cleave, and then you go straight in. You never touch the fiber after you cleave it. So, repeating, it's going to be stripped, cleaned, and cleaved. Then it will be inserted into the back of the connector and mechanically secured. Boom, done. And it probably takes not much more time than it took me to just say it. The thing is, they cost money. In fact, they cost a pretty good amount of money. I think I've seen estimates where they're like $20 as opposed to $2 for a standard epoxy connector. But the time savings from what I just described versus all the polishing and everything that goes with the epoxy connectors, in certain applications I can see how they would be beneficial. They are going to be a built-in point of failure, and they are going to have higher reflectance values than a directly polishing the end face of the glass. It's a mechanical connection. We're essentially putting a mechanical splice inside a connector. So we're going to have more reflection. There's no way around it. And because it's a mechanical connection, it's ultimately going to fail. So you got to weigh out the time savings and the cost effectiveness, which that is certainly it exists. Paying a technician to polish, 24 connectors, and it takes, better part of a few hours or you can do 24 of these in 30 minutes or an hour at the most. So you've got some time savings, that is for certain. And however much you're paying your technician to polish, you're saving that money. So that's going to balance out. You just got to look at, they're going to fail. You're going to be replacing them every 6 months to a year. And they're going to add reflection. But if you can handle that in your loss budgets and handle that in your monetary budgets, they're certainly quicker and more painless out in the field, particularly out in the field. Field polishing is brutal. So I guess there we are. Now, connector polishes. Once the optical fiber is terminated, in this case we're going to be talking about the epoxy, whether it's two-part epoxy or hot melt. Once the fiber is secured to the inside of the ferrule and the glass are going to be polished. There are 5 different polishes. There's one of them actually missing from this slide, but it's on the next one. And I'll save some of my comments for the next slide. But the idea here is that all of these different polishes reduce back reflection. And that is becoming more and more huge as we move into higher speed data rates and higher power lasers. All right, here's the list with all 5. Once upon a time, back when the dinosaurs roamed the earth and I started working with fiber, we had flat polished connectors. And all we did was just polish it. There wasn't anything fancy about it. It did the job. You know, it did the job back then. I mean, we had low data rates. We were reprocessing our signal every 80 kilometers or so. And, you know, we got by with it. Now, I did have significant back reflection, but it didn't really matter. I mean, we were using low power lasers, low data rates. It worked. Well, we start getting higher data rates. We start needing to reduce that reflection. Any little piece of dust in that flat polished connector is going to cause an air gap. So the new design rounded off the corners. So instead of it being flat straight across, it just rounded it off a little bit. And that allowed some of the dust to shunt out to the edges and still maintain physical contact at the glass surface. In fact, it sounded so good, they decided to call them physical contact connectors, or PC connectors. Well, of course, if, you know, PC is good, then super's better, right? So the next generation of connectors was rounded off even further. It was kind of a high radius dome. It still had the ceramic ferrules were in use then, and it reduced back reflection down to negative 40 dB. And that actually gets into a usable range nowadays. Well, of course, if super's good, if super's better than PC, well, then ultra must be the best. So they went to a higher radius, actually a smaller radius dome. It is completely curled, rolled off on the end. And you can see from the image, these are fairly accurate images. Here we've got that high radius arc for the doming. Here we've got a much smaller radius. And the whole end is domed over. That dropped back reflections down into the neg 55 range, which is pretty small reflection. And it's a little blip on an OTDR trace. Then it was discovered that if we angled the end face 8 degrees, we could cause the back reflections at the air glass boundary to go back in at an angle, bounce around a good bit more, be absorbed by the cladding, or escape through the core cladding interface. And back reflections were reduced down into the -70 range. -70, you just about need the OTDR to tell you it's there. I have honestly shot through APC mated pairs that the machine didn't even know were there. The computer and the OTDR didn't even see them. They're invisible. And most of the time you see the slightest little blip, but it is insignificant. And those of you that have done testing, you're used to that characteristic end spike on a patch panel at the other end of your link. You're not going to see that with an APC connector. If it's terminated to APC on the other end, it's more likely going to roll off. It'll just fall off into the noise, and you won't see that characteristic end spike. Now, all of this was done to reduce back reflection and optical return loss. Now, optical return loss is basically any light reflected is not going forward. And with the high-speed data, high-power lasers, any kind of reflection is becoming a problem, because we get any kind of ringing in there. A high enough power laser can cause that light to bounce 2 or 3 times. If we're throwing ghosts out on the trace, then we've got bad reflection, and that's going to show up as bit errors, and ultimately the link is going to fail. Now, next month we're going to be talking about cleaning, but I'm going to mention one thing now, that optical return loss is usually a function of not having the connectors clean enough. And the connectors themselves are capable of very low reflections nowadays, but we have to make sure they're cleaned. And I will tell this story again next month, but we were out on a job where links were failing all over the island, all over the country of Haiti after the earthquake, and they thought there was actual fiber damage from the earthquake. We started shooting for loss and started looking at optical return loss, started cleaning our connectors, and we had to replace a few patch cords because the connectors were damaged. But we started cleaning up, retested, got our return losses down, and then the technicians start calling us and saying, "What did you guys do?" Well, it turns out that all we did was clean the connectors, and all of their links came back up. So I'm going to tell you that reflection matters. So you want to look at your reflections, you want to look at UPC or APC connectors. Keep that reflection down and tune in next month for us to talk about cleaning, because that's the other critical component that goes with connectors. And just so that we know that it's an angled connector that we're playing with, we're going to throw a green color on it instead of the blue. And again, I'm going to finish up talking about APCs. -70, return loss, some of them are even invisible. Used in CATV, FTTX, and testing applications. Less back reflection, has the green body and sleeve. They're a little more costly because the jigs necessary to put that angled polish is a little harder to work with. But it is absolutely the best performance of any of the small form factor, or any of the connector polishes rather, and is going to be well worth the little extra cost. So with that, I'm going to check out the question box in the GoToWebinar window and look at a couple of the questions that have come in. Now let's see. Here we've got a question. What type of end face does an SFP laser typically have? Can you use UPC or APC to plug into them? Now, in my understanding and in my experience, those SFPs typically do have a UPC connector. Most of them are LC. They're using the small form factor because this is plugging into a switch. I do believe that it is possible to get them APC, but the ones I've seen typically are going to be UPC connectors. Let's see, now here's someone that has plenty of plastic connectors in their patch panels, and they're wondering if using a patch cord or jumper with ceramic connectors, would that cause, would it increase the loss, or and what would be the, I'm not quite sure what the rest of the question is. No, it should not change your losses. Plugging a ceramic ferrule into a plastic ferrule is not going to have any effect. The plastic ferrules, when I say plastic, I'm not talking about a kid's toy kind of plastic. I'm not talking about the kind of plastic that your phone on your desk is made out of. I'm talking about a very, very dense, very hard polycarbonate type of plastic that polishes smooth with the same glass, the same abrasive sheets that we use to polish ceramic. That gives you a clue right there. We use the same polishing abrasive films to polish this plastic connector that we do to polish a ceramic one. That's how hard it is. So putting one of each together at a mated pair shouldn't have any real effect, or at least none that I am conscious of. All right, let's see, another question. Do I think that the quick connectors have a place, or should they only be using polished or fusion spliced? Well, in truth, I've got to own up, I don't like quick turn connectors. I think that they're a built-in point of failure. I can see how they can be useful in certain applications, but I will honestly tell you that my preference is a splice-on pigtail. And you can buy a pigtail set that's factory polished. It's got all of your documentation. It's going to have the lowest loss, the lowest reflection, because all the work was done in a factory. And then it's got a certain length of fiber that you simply fusion splice onto the end of your glass. And in every case that I've worked in the field, I have terminated to pigtails. I will be honest, I've never done a field polishing of a connector, and I very rarely used a quick turn. The bulk of my work has been entering buildings and going to a transition box and splicing on pigtails and making the transition to inside fiber at that point. And I just think that's the best way to go for single mode fiber. We keep reflections down, we keep losses down, it's good and solid, and it's not going to go anywhere. So since the question asked for my opinion, that's where we are. Now, the APC connectors, are they ferrule? Are they ceramic? Are the ferrules ceramic? And the question is, most of them, yes. There's really a short answer because, yeah, the biggest bulk of them are going to be ceramic. And that's pretty much what we got there. Are there any Are there any performance limits on small form factor connectors versus the standard connectors? Not with the LC. The LC has very low loss, very low reflectance, comparable to an SC connector, and those two together probably are the best connectors out there for performance standards or specifications. And then the last question we've got. Someone's asking me to recommend a fusion splicer. And that is a little outside the scope of this webinar, so I'm going to ask that if you're interested in talking to us or interested in talking to me about a fusion splicer, I'll be happy to talk with you on the phone. And you can call into our number at 877-529-9114. When the automated system kicks in, you can press 1. That will take you to sales. If you get to the sales department and you want to specifically speak with me, just tell them that you want to talk to Terry, and they'll find me in the building somewhere and get the call transferred over to me. So I want to thank everyone for attending today. We're honored that you are here, that you've taken time out of your day. You had a choice of how you were going to spend this time, and you chose to spend it with us. And we appreciate it greatly. Look in about a week for the recording of this, and I guess that's about it. So everybody have a great afternoon or good whatever day part it is for you, wherever you're listening. Thanks a lot.